Okay, good morning, everybody. Welcome back to virtual seminars in Precambrian geology for the fall season here. We're starting off with presentation from Ross Mitchell. And so I want to take a little bit of time to just remind everybody that we have a website everybody can visit to, and I'm going to show that on my screen really quick. So here's our website here. It's a Google Sites. Here's the homepage, virtual seminars in Precambrian geology. We have a quick information on us, and right below that information, we have directions on how to participate. It's kind of, since it's through the university, it's a little bit unconventional, but you basically just send an email to the listserv with subscribe in the subject line, and that's about it. And then plenty of other information can be found here. Also, I would like to draw everybody's attention to the code of conduct up here. Everybody's expected to look through this, and every time you're joining a meeting, you're basically just signing an agreement. That's how I consider it, and I don't have any problem pushing people off the meeting, etc., speaking over people if we can't stick to these, but we never really have too much of an issue. Also, we have the schedule. That's the calendar here, showing everything through December right now. And as Andre and I fill up for next year, you'll be able to see some of that probably a bit ahead of time. And then every week I keep the speaker bios updated. I have the next seminar always posted, usually by the by the Friday before, depending on if I have the information or if Friday was a holiday or something, etc. And you can see some of the past seminars, and I try to post the links for their recorded ones on YouTube. Importantly, everything is posted on YouTube. So lastly, really quick, you can also go to nominate a presenter page, and you can nominate yourself, you can nominate others, and that you would like to hear from to help us to populate our series with people you'd like to hear from. So with that, after Ross today, we'll continue to have regular seminars every Thursday at 8 a.m. And with that, that's all I'd like to say. And Andre, could you please go ahead and introduce Ross for us?
Yeah, it's a
And
pleasure.
Ross, you can go ahead and share your screen. Sorry.
So it's a pleasure to introduce Ross Mitchell. We all drawn to academia, but it's provide unconventional pathway. But it seems like at some point this way changed, and Ross represent exception to this general pattern. So maybe because in childhood he traveled and lived in France with his parents, and where he got some of French he still using. So Kent finished the bachelor degree in Carleton College. It's a place where many geologists came from. He then followed to Yale University, where he did PhD with David Evans and worked on Paleoproterozoic, I guess Neoproterozoic, Paleomech, and parent polar path and various other things. He did postdoc at California Institute of Technology, I presume with Joe Kershing, but I might be wrong. And then he followed to Curtin University, where he was a research fellow for 3 years with Professor Lee. And after it, he took unconventional step going to Institute of Geology and Geophysics in Chinese Academy of Sciences, where he moved from associate professor to full professor. And that's where his productivity really picked up with multiple papers on multiple topics ranging from plate tectonics to sort of astrochronology to various glaciations in Mid-Proterozoic and so on. Another quite unusual step he took, he published in 2023 book, Next Supercontinents, Solving the Puzzle with Future Pangea, a step that normally in academia we are told that in sciences, if you write a book early in your career, it's sort of could lead to the end of career, but apparently Ross survived and did pretty well. And it's a pleasure to introduce him, talking today about this, what used to be boring, but he suggests should be called balanced billion. So the floor is yours, Ross.
Wow, Andre, thank you very much. I've never had an introduction that went all the way back to my teenage years, so my parents will be happy for the shout out to France. And also, thank you, Alex. This seminar series has been a great resource for me and for my students. We're crawling the YouTube recordings all the time. So thanks a lot to both of you and the community and the audience today. So the balanced billion, rebranding the extended odd mid-Proterozoic interval of Earth history. As Andre mentioned, I did my PhD with David Evans, and this is kind of an exciting day today because David and I, we've worked a lot in the past, but it's been a few years since we kind of put our heads together formally. So I'll kind of tell the story about how this idea was hatched, and Andre plays a role in that. So here, Andre and I are in Morocco this last summer. There was a nice confluence of the Rodinia meeting from IGCP in the past and Richard Ernst International Dike Conference. And so Andre, I obviously knew his work for years, knew his work over COVID with this great seminar series, but it was great to meet in person, and that's why I'm here today. And again, thanks to Alex as well. Here's Andre on the right, and my co-author here, David Evans, on the left. In the center is the king of Moroccan geology, okay? And we had a great conference, and Nasser Yubi. We had a great conference, and then we also got to do some great field work together. This is a nice shot from the conference where Andre was supposed to be hosting a session, and luckily David decided to join him. So when Andre fell asleep, David was there alive. And to join us as well, since I'm talking to Riverside, we were graced with Tim Lyons' presence. He joined the end of the conference to give us an update on the oxygen story, and then was luckily able to join us as well for the post-conference field trip. Here we're checking out some neat relief on some cross-bedding and ripples. And it was a great exchange between my Chinese colleagues, many of which were able to join, and Andre, Tim, Dave, and the whole crew. So my Carleton advisor, since Andre luckily mentioned Carleton College, always told me to tell them what you're going to tell them. So here's, here's the spoiler. Here's the forecast. I'll go through all the data sets on the right, kind of one by one. But the forecast is whether you look at surface processes with paleoenvironment, to ocean proxies, to crustal, to mantle, and even core proxies, the mid-Proterozoic, after the early Paleoproterozoic and before the kind of mid-Neoproterozoic, the mid-Proterozoic, including all of the Mesoproterozoic, is really bizarre. And I'm kind of, the whole point of today's talk, I want to manage expectations. I won't be providing a whole mechanistic view of the world. Hopefully, as a community, we get there in a few years. But today, it's just kind of, is that real? Is there something happening on Earth during this time that deserves having a special name. Okay, we all know the Great Oxygenation Event. We all know Snowball Earth. We all know modern style plate tectonics. These are, benchmarks, landmarks in Earth history. Is the boring billion one of those benchmarks? And if it is, we should probably get the right name for it. And I'll kind of talk about why there's a little dissatisfaction in the community, why boring may not be right, and propose with David that this phrase balance might be a better concept. And I should mention that in the chat window, okay, I've posted it right now, the link to the preprint, okay? So you can see these data sets, see where they come from, and investigate them yourself. So before we jump in, as Andre said, just a little advertising. My publisher would be sad if I didn't. During COVID, a little COVID project, I spent about a year researching, or a year proposing, really, a year writing, and a year in production, about 3 years total. This popular science book, if you do look at the reviews or talk to people who've read it, it's probably more emphasis on the science than the popular, which is good for all of you guys and gals, because it's really, I think, the people on this call are kind of the target audience. It's very much a university press book. And I suggest you, support the press, buy it from the press if you can. And I would really appreciate if you take 5-10 minutes once you've read the book to write a review on Amazon or Goodreads. It's basically, most of it, 80% is about the past. Starting with Pangaea, the most recent supercontinent, going back to Rodinia, and then back to the Paleoproterozoic with Columbia Nuna, and then learning what we have from the past, then kind of looking more speculatively to the future about the next supercontinent, given that the supercontinent cycle is likely to continue for a few cycles. And also a little quick advertising. Andre mentioned that I'm in China and working with the Chinese Academy of Sciences. It's as of next month, I will have been here for 4 years. And I've, very thankful from the government, from the Chinese Academy of Sciences, from my institute, multiple sources of funding. I've built up a little bit of a lab, and I kind of think of our lab as a mini geology department. So of course, one of my students is in paleomag, my chief expertise, and one of my students, Chan Fang, is in cyclostratigraphy, sedimentary rocks. But we really have a group from all over the Earth system. So one sedimentary student, a metamorphic student, an igneous student, paleomag from the geophysics side, a geochemist from the geochem side, and one student, Zhang Jilian, doing machine learning. So obviously I have to provide them with other co-advisors and other students to help their expertise. But as a group, I think they're able to interact in ways that the Earth actually interacts, as we'll talk about today, as an interdisciplinary system. So the boring billion, just to get everyone on the same page. I know folks like Andre and my co-author David, who were part of the Graham Shields's green paper about, largely on the Mesoproterozoic last year. We're well versed in where this term came from, but I just want to get everyone on the same page. Where did the term boring come from? Well, the data comes before the name. So Martin Brazier, the late Martin Brazier, and with his son now, Alex Brazier, still continuing in geology. Brazier and Lindsay had a geology paper in the late 90s, and Roger Buick and others kind of followed up on this, where they found when they did carbon isotopes through the well-preserved MacArthur Basin of North Australia Craton, they didn't find what you typically found in the Neoproterozoic or the Paleoproterozoic with these carbon isotope excursions. So they were kind of the first to point out this potential environmental stability. Now, they had an ecological, and they did link it, to their credit, to potentially a long fuse, a delayed response in the evolution of eukaryotes. Now, they have an ecological explanation for that. That's somewhat fallen out of favor, but this is still an open question, so maybe even worth revisiting. But the word, apparently Roger Buick was using the phrase boring in conferences and informally, but to my knowledge, the first published mention of the word boring billion comes from Heinrich Holland, Dick Holland at Harvard at the time, where he kind of breaks up Earth history into 4 stages, Holland being one of the big early proponents of the great oxygenation event. And in between this GOE and this Neo-Proterozoic rise to more modern levels of oxygen, there was, as he said, an apparently rather boring period, okay? And he knows that, of course, originally this period was kind of flagged because of its lack of carbon isotope excursions. So Holland also points out, in contrast, this nice figure from Galen Halverson, which has been obviously updated over the years. Unlike the Neo-Proterozoic, with these really dramatic negative carbon isotope excursions, the Shuram, the Trizona, the Bitter Spring stage, unlike that, and unlike the Paleoproterozoic with the positive, massive Loma-Gundi-Getuli excursion, the Mesoproterozoic and the Mid-Proterozoic really didn't seem to have anything like that. And Holland went one step farther in providing this nice plot of manganese deposits, which are occurring as crusts on the seafloor. And from a manganese perspective, this period's boring. There's a lack of manganese deposits. And that's a common theme that we're going to come to with rock type after rock type throughout this talk. So I'll kind of check in as we go proxy by proxy. So David and I have outlined these proxies roughly from shallow or high processes in the atmosphere down to deeper processes in this figure. So just to summarize where the phrase originally came from, it really came from shallow processes, specifically the ocean, the atmosphere, where there's no carbon isotope excursions of large magnitude, and there's no OOEs. That's an oceanic oxygenation event. Now, there are oxygenation events and there are excursions, but relative to the magnitudes we see before and after, they pale in comparison. So let's look at the other surface processes that have kind of come to light since the establishment of this concept of the boring billion. And let's first look at life, because even from the first paper from Brazier, there was already this interesting idea that maybe this boring interval might be helpful to explain why animal life took so long to reveal itself in the late Neo-Proterozoic and really Phanerozoic. So Andy Knoll, of course, Harvard, has a nice timeline, timetable of evolution. I would just point out, so he's got, the oldest known eukaryotes. Gunflint's a little bit older, but that's a little uncertain. Here in China, we have very well preserved eukaryotes around 1.6. But if you use molecular clock data, the divergence from cyanobacteria to multicellular eukaryote life does arguably occur as early as 2.1. Okay, so we don't get fossils, at least known now, until 1.6, but molecular clocks put that divergence earlier. And then, I don't want to diminish anyone working on Mesoproterozoic sequences. There's a lot of fascinating work being done, but at least by current knowledge, the concept of eukaryotic diversity really doesn't increase by current knowledge until late Neoproterozoic. So on the right, I've shown a nice example from a primary productivity point of view by Joachim Brox using biomarkers, where you really have a cyanobacterial world up until the snowball cryogenian glaciations, where Joachim has shown quite nicely this surge of phosphorus and nutrients allows a different type of primary productivity, namely a eukaryotic primary productivity, red and green algae, to finally take hold, leading to this modern world. So in terms of diversity and in terms of the ecological dominance, even though eukaryotes existed and diverged before the boring billion, they don't really take off ecologically and in terms of diversity until later. So can the boring billion explain this long fuse of life? That might be its most important aspect. And then let's continue with our surface processes, looking at the cryosphere. Probably most of the people in watching this seminar in the past already know this. We have the well-established cryogenian, Sturtian, and Marinoan low-latitude, globe-girdling snowball Earth glaciations in the late Neoproterozoic. And Dave Evans's PhD work established very nicely with Joe Kirschvink that at least one of the early Paleoproterozoic glaciations, the Macchigneni, was a low-latitude glaciation, possibly like a snowball Earth, but in the Paleoproterozoic. And the Phanerozoic glaciations, the large ice sheet spanning across much of Gondwana, and the Cenozoic, Antarctic, and Laurentide Fennoscandian ice sheet in the northern hemisphere, everyone's quite well aware of, the Pangola in the early Archean, but in the middle, there's nothing. So there's what Paul Hoffman calls the Proterozoic glacial gap. And then Noah Planovsky has a nice plot kind of picking up where Dick Holland had left off, showing that phosphorites, which again are going to be related to photosynthesis because it's a nutrient, but shows that again in this gap, in this middle period of time, there are some, but a lull in phosphorites. So just summarizing, we've dealt with now all of the paleoenvironmental proxies at the surface I would refer to. We've dealt with the atmosphere, the oceans, the original ideas behind the boring billion, and now decades later, there appears to be a boring billion in terms of both the biosphere and the cryosphere. Eukaryotes diverge and are found as fossils, but they don't diversify until a billion years later. We have low-latitude glaciation in the early Paleoproterozoic, but we don't have low-latitude glaciation or arguably any glaciation until the late Proterozoic. So in this middle interval, there's limited evolution and limited glaciation. Now let's keep going farther. I really I attribute a lot of this to Nick Roberts's work at the British Geological Survey, BGS. He kind of was, to my knowledge, one of the first people to connect potentially solid Earth crustal tectonic processes to this growing concept of the boring billion. Of course, the pendulum starts swinging, and it swings quite far. Bob Stern, to his credit, really stirred the pot, as he always does. Science needs that. In my opinion, a little too far, where he went so far to say, if you have sluggish tectonics, maybe tectonics was not active and it's a single lid. But to his credit, Bob, evolved from his late Neoproterozoic onset of plate tectonics to accept a Paleoproterozoic phase of plate tectonics. Only in this new iteration, he argued that in between the early Paleoproterozoic phase and the late Neoproterozoic modern phase, that plate tectonics basically shut down. more like a Venus stagnant lid. So Nick Roberts, staying on task, kind of fired back and took a very even-handed approach where, really tried to see if he could rule out, reject the null hypothesis, if you will, of a stern single lid. And we end up preferring a plate tectonic example. But I would just point out that a lot of the data sets we're using in our paper are the same data sets as Bob Stern pointed out. The lack of ophiolites. If you have active plate tectonics, and plate tectonics, like we know in the Tethys, you should preserve ophiolites. No? Well, in the Mid-Proterozoic, we only get them until around Grenville age. And Mike Brown's database shows that there's very few occurrences of high pressure metamorphism. I'll touch back on that a little more. But in addition to these absences, I'll also point out at this stage an occurrence. So there's an anomalous occurrence of anorthosites, and we'll talk about this more. So I'll just tease you there. And let's go further. Richard Ernst, Wouter Bleeker, and team had a nice paper, Nature Geoscience, showing these large igneous province barcodes have a very strong match between Laurentia and Siberia for over 1 billion years. So they argue for this long-lived connection. Dave Evans then showed later with some Russian colleagues in the center plot that when you match the paleomagnetic poles of Laurentia and Siberia, again, over that same time interval, with only 1 or 2 exceptions, the poles of the same age typically overlap. So it's hard to justify much or any mobilism between Laurentia and Siberia during this time. And the last thing on the left, it's a little bit complicated, but just look at the like-kinded colors. So you'll notice the 2 positions of green, Baltica, are quite similar. They're rotated, but it's along the same margin from one supercontinent in the Paleoproterozoic to the next in the Neoproterozoic. Likewise, the positions of West Africa only is slightly changed, Australia only slightly changed, Amazonia only slightly changed. So was there in this supercontinent cycle something different than what we saw between Rodinia and Pangaea? Were there some elements of incomplete breakup, like Siberia and Laurentia, or the failed rift of the mid-continent and Laurentia itself? Or were, in the case of Baltica in this rotation, when there was plate reorganization, was it relatively small ocean basins being opened and closed? Now, I believe my co-author would want me to just emphasize that we don't want to throw the baby out with the bathwater. We are not, we want to make clear what the Mid-Proterozoic from a tectonic perspective is not. And we like this quotation from Paul Hoffman in his annual reviews called Big Time, where Paul said, recent suggestions that Nuna Columbia supercontinent and Rodinia were one and the same make a mockery of the Grenville-aged orogenic belts and their role in Rodinia assembly. So kind of 2 papers, Tong Ming's work in Science, where he refers to orogenic quiescence during this time, and the aforementioned Bob Stern's work, where he goes so far to argue for a single or stagnant lid situation. We just want to distinguish what we're saying about potentially this super cycle being different from those end members. But that being said, there are some peculiarities in this supercontinent cycle. As I just kind of mentioned, you'll see many similarities in the reconstructions of supercontinent Columbia or Nuna and Rodinia, namely that Siberia connection we talked about. And I'll draw your attention to another paper that Zoyi, who's on the line right now, one of my colleagues at IGG, just became an assistant professor last year, His EPSL paper with myself and Mike Brown, who's joined us today as well, in addition to the lack of high pressure metamorphism during the Mid-Proterozoic, there's an anomaly in the cooling rates, okay, in the exhumation rates by extrapolation of metamorphic rocks. So in this paper, we kind of point out that some kind of sub-continental warming that is affecting metamorphic cooling rates seems to be very different in the Mid-Proterozoic than either before and after. And when you plot up those cooling rates side by side with these aforementioned surface paleoenvironmental proxies, the timing does seem to be there. So just to summarize at this point, the crust and the tectonics seem to have some anomalies too. The boring billion isn't just boring in terms of shallow processes. There's very few ophiolites, there's very few passive margins, there's very little to any HP, high pressure metamorphism, and arguably limited plate reorganization compared to the Orosirian in the Paleoproterozoic and Gondwana and Pangaea in the later Neoproterozoic, Phanerozoic. So let's continue even deeper. But before we do so, let me kind of circle back to the whole point of this talk. Reasons for rebranding the boring billion. Anytime a brand needs rebrandings for various reasons, I won't go into that. But for our case here, the interval is still important and arguably, based on the proxies we just saw, well beyond the initial vision of Holland and Brazier, I would argue even more important. So it's worth reclaiming that brand. Some of us my age or older may have loved Legos growing up, but believe it or not, there came a time when children didn't really like Legos. Now children again love Legos, and I'll mention why that is. So when you have a great brand like Legos, it's worth reclaiming. And I'm arguing, even though I don't like the name, I'm arguing based on these proxies that the concept, the ideas behind the boring billion are worth reclaiming. But the term boring is subjective. What you think is boring, I might think is exciting. What I think is boring, you think is exciting. And it's really ripe for straw man media article after media article. Oh, geologists discover the boring billion is not so boring, over and over. And the alternative, Earth's middle age, is also a misnomer. Earth is 4.5 billion years old. So it just isn't the middle age. It's far too young for that. So arguably a new concept is needed. Around 2003, when the Lego brand just stagnated in terms of sales, and they realized from their surveying that children, their obviously most important demographic, children weren't into it, they realized they needed a new concept. And they put more emphasis on the Lego movies, the Lego theme parks, and social media. And as you can see, you invigorate the concept behind your brand and you reinvigorate sales. In our case, I would argue if we get past this silly name, we're going to get more and better science and more people excited to work on this interval. So you need a testable hypothesis in science, and boring is not a testable hypothesis. So based on 2 papers of mine over the last 2 years, Dave Evans helped me realize at this conference in Morocco that we have a new concept that people can actually test. And it's a concept, instead of boringness, it's a concept of balance. So the first paper I'll bring up is based on Earth's rate of rotation, which controls the length of day, okay? When the moon formed, obviously based on the moon forming impact hypothesis, the moon was very close to Earth, and now the moon is far away. So the moon has gotten farther and farther away over time. In doing so, in boosting itself, how did it boost itself to a higher orbit? It did so by stealing rotational energy away from Earth. So by the moon boosting itself to a higher orbit, the Earth's length of day has gotten slower and slower and slower over time. Now, most models think that that is basically a more or less linear or kind of smooth evolutionary path. But then there's another hypothesis published in Precambrian research many decades ago by Kevin Znali, and then picked up years later by Dave Stevenson at Caltech, where they point out that even though you had the lunar tide pulling gravitationally on the ocean, which is slowing Earth's rotation, that's the mechanism by which the moon is stealing the rotational energy. There's also solar tides, okay? You have namely two gases, ozone and water vapor, that during the day, as the sun heats up the atmosphere, expand, and you actually have an atmospheric tide, and based on the orbital configuration, whereas the lunar tide is pulling, slowing Earth's rotation, sense of rotation down, the solar tide is actually accelerating the rate of rotation. I put pull and push, but that's simplistic. They're really both pulling. It's just really one's a decelerative torque from the moon and one's an accelerative torque. Now, if you go farther back in time, this is what Kevin Znali realized. If you go farther back in time, when the lunar tide, when the moon was closer to Earth and Earth was rotating much faster, that frictional coupling would have been much less. So the lunar pull would have been weaker in the past. So although the solar tide today is too weak to really matter, what Kevin realized was that there could be a time in the past when the lunar tide was small enough that the push and the pull, would have actually been balanced. And this, of course, depends on atmospheric composition as well as surface temperature. I unfortunately don't have time to go into that today, but please read my Nature Geoscience short paper, which delves into the atmospheric implications, what had to be the case for the resonance, and how the resonance itself might have actually influenced the atmospheric evolution. So, we just realized, while I was a postdoc at Caltech, I knew through Stevenson's work, I knew of this idea, but there really had never been enough data to test it. And so what my co-author, Uwe Kirscher, and I realized was, given the proliferation of cyclostratigraphic data, we could test it, because the precession component is directly related to Earth's rotation. You can actually convert your precession period measured with cyclostratigraphy to calculate Earth's length of day. And there's other means, tidal rhythmites and stromatolites. But the cyclostratigraphy, really the proliferation of the data in the last 10 or so years made us realize, hey, there's enough data, let's test it. And doing a simple statistical step change analysis, change point analysis, where you're basically, can you reject the null hypothesis of no change? And in fact, we could not. Not only could we not reject no change, in fact, what you get is this three-step pattern, which matches quite remarkably with the completely independent theoretical concept of Kevin Znali and Dave Stevenson. So Earth's length of day seems to have paused. Instead of getting longer and longer, during the boring billion of all times, it stopped getting longer. And no joke, completely independently of us, I believe a week or so later, published in Science Advances, there was another group largely doing modeling again, independent from us, which was largely empirical, and they almost got more or less the same result, 19 and a half hours with a little longer interval. Now, I don't want to give the impression that this is a done deal. As of, I believe, 2 or 3 days ago, Jacques Lascar from his group in Paris has posted a preprint questioning some of our work and questioning some of their work and another paper. So, you know, I don't want to give the impression there's consensus. Definitely more work needs to be done, which is great for all of the students who are on this call today. So to summarize there, even if I didn't know where to put the Earth-Moon system, so I just put it really high up in the plot. And this stabilization period coming from theory and from data around 19 and a half hours, the stabilization period in Earth's rotation appears to have occurred also during this time interval. Now, so, you know, that's the first time this balancing idea kind of, oh, the solar torque and the lunar torque might have balanced to stop Earth changing. Balance. Now let's go deeper, okay, into the mantle. This is a little more into a little geophysics. Just a quick shout out to the innovation. It's kind of like the science or nature of China after only 3 years, impact factor over 20, and have an innovation geoscience sister journal as well. So we have this paper, again with Mike Brown on the call today, Evolving Mantle Convection from Bottom Up to Top Down. So convection must be mass balanced, but it doesn't have to be force balanced, okay? You can have stronger upwellings, which is typically referred to as bottom up, or you can have stronger downwellings, which is typically referred to top down. And it's really the temperature difference across your top and bottom boundary conditions. In the case of the mantle being the CMB, core mantle boundary, and the LIB, lithosphere, asthenosphere boundary. And those boundary conditions will control whether you have convective symmetry or asymmetry. And we said, okay, are there some mantle-derived melts that could give us a clue about how Earth's convective symmetry or asymmetry has evolved or not over time? And just very briefly, komatiites being the hottest lavas on Earth, given their high MgO contents and their spinifex textures, we interpret, along with others, as a kind of plumes-dominated or bottom-up convection period. And although there's one occurrence, the Gorgona, in the Cretaceous, there's really no komatiites after the Borean Billion, okay? And kimberlites, okay, and everyone knows kimberlites from their diamonds that they bear. The huge kimberlites are very much related, obviously, to lithospheric processes, since they're lower lithospheric processes, and again with their MgO values, mantle-derived melts. And most kimberlites are young. It's almost like the opposite of the komatiites. The Mesozoic kimberlite bloom is off the charts, okay? And so we take kimberlites as a typically top-down convective source. Interestingly, between the two, there's this lull. There's no komatiites, there's very few kimberlites. And to the rescue come anorthosites. And just simplistically, these plagioclase rich magmas, high in aluminum, kind of these basalt pond at the base of the moho, and after fractional crystallization, differentiation, you get these beautiful white and black rocks. And I've excluded the megacrystic Archean ones, just looking at the massif style anorthosites. And wow, they're really not convincingly connected to plumes, and they're really not convincingly connected to subduction zones. So they're neither top down or bottom up. Maybe anorthosites and this mid-Proterozoic bloom are the time between balanced convection. So if Earth was dominated in early Earth, during hot early Earth, by upwellings, strong upwellings, And in more recent times, dominated by strong downwellings, it therefore supposes that in between bottom up and top down, there had to be a period where convection in the mantle was relatively balanced. And so this is basically over time using these mantle melts. We're arguing from komatiites to anorthosites to kimberlites. You see the evolution from bottom up to symmetric to top down, with this boring billion occurring during this time of balance in the mantle. And from true polar wander, which is the wholesale rotation of the solid Earth, the crusted mantle, if convection in the mantle was balanced, you should not have much true polar wander, because true polar wander is driven by the largest masses on the Earth, those being in the mantle. And Chang Wang and I have a nice review paper in both Chinese and English, I believe last year. And as of yet, there are no uncontroversial, large, rapid TPW events during the boring billion. So this would tend to agree with this concept that mantle convection might have been relatively balanced in its upwellings and downwellings during the boring billion. So there we have it. And as you see, that phase of anorthosites, the anorthosites era, again, kind of plots more or less on top of this mid-Proterozoic enigma. And lastly, from Paleomag, a lot more work needs to be done. Let's look as deep as the core. Everyone knows the geocentric axial dipole, okay, inclination measured paleomagnetically can be converted by the latitude equation there, dipole equation to latitude. And here, Laurie Peasant and colleagues have shown quite enigmatically again that the average inclination of all high quality paleomagnetic data, the average inclination through most of Earth history and Proterozoic is spot on what we expect of a geocentric axial dipole. But during this, this is his binning of the data, completely independent of us, in this blue interval, whoa, we're almost 10 degrees or so lower inclination. And this nice little plot from Dave Evans's evaporates paper in Nature, showing how if you take an inclination and you ramp up not the dipole component, but the octopole, a higher spherical harmonic of a magnetic field. And as the octopole gets stronger relative to your dipole, maybe you can actually lower the average inclination. So is this because continents were just at lower inclinations, or is it some magnetic field thing that is yet to be shown? But once again, when we find a proxy for the core, this being one of the most abundant, the inclinations from paleomagnetic data, wow, that anomalous enigmatic interval of the middle, as Laurie Peasant called it, kind of plots more or less again on this time period. So here's the case, the reasons for the balance billion rebranding. Balance, first of all, is true to the founding principle of the relatively stable carbon cycle from Brazier and Buick. Second of all, balance incorporates evidence for the stable rotation, the solar and lunar torques, and the mantle convection, the balance between upwellings and downwellings. And possibly most importantly, especially for the folks on this call, is the future. Is balance a concept, a testable concept of more measured global change that may help us interpret these many other proxy oddities? Why are there no ophiolites? Why are there few passive margins? Yada, yada, yada. And the last kind of implication, zooming out for a second, maybe this interval, if it's truly a period of more measured global change, maybe this interval provides a helpful model for modern climate change with increasing extremes of both hotter and colder and wetter and drier. Maybe by studying the Mid-Proterozoic, we might actually get some geoengineering ideas for how to build a more balanced planet. And just again, a little shout out to my book. Thank you for those of you on the call that were involved in it. And again, if you do like the book, please consider taking some time to do a quick review. That helps get the word out. And the last thing I'll do, I don't know if this will work, but I figured, why not create a little survey, okay? So while we're answering questions and talking, I'll just put a link in the chat window, okay, where you're gonna see a survey through Google Forms like this. And we'll just do a little quick straw poll just to see how people feel, and the results of that poll, maybe Alex and Andre can consider sharing on the website. Or it's basically a simple question, yay or nay: should the boring billion be rebranded the balanced billion? Yay or nay? Yay meaning I prefer what Ross and David said about rebranding to the balanced billion, or nay, I'm fine with the boring billion. So with that, I'll thank you very much for the opportunity, Andre and Alex, and the distinguished audience. And I'd be happy to answer any questions you may have. Thanks, guys.
Great, thanks a bunch, Ross. Really good. Let's switch to our question discussion section here. And what that means is you're welcome to ask Ross questions by either raising your hand, which you can find the raise hand at the bottom of your screen. We already have one up. I did have someone send me something in the chat before hands went up, so I'm going to address that first, but then we'll get to hands. But yes, so you'll go to the bottom of the screen, find reactions, click the up arrow on reactions, and select your hand gestures. And well, it became a little bit more complicated. Okay, raise hand is there if you click reactions. All right, let's see. The first question I got was from Case under Sarwan. Does the snowball Earth phase right after the now balanced billion time frame occur due to the imbalance between the tidal torques after a long period of stability? And would the balance between the tidal torques contribute to weaker jet streams and thus further influence climatic conditions? Should I send that one to you so you can read it?
That'd be great.
All right. Also, it's preferred to send in messages to everyone if you're going to ask a question, so we can read them. We can read along. But there it is for you.
The snowball Earth right after the occur due to imbalance between tidal torques after a long period. Wow. Okay. So actually, Dave Stevenson's paper thought about the snowball Earths being a cause of ending the resonance with the high temperatures in the associated cap carbonates kind of kicking out of the resonance. But what you're asking is, is snowball Earth an effect of the resonance? I've never thought of that before. There's no short list of reasons for what caused snowball Earth. So I would definitely encourage you to, consider that.
All right. Great. The first hand that went up was Daniel Segessenman. Please go ahead and unmute yourself. Sorry if I butchered your name.
No, you got it exactly right. Thank you. Ross, great talk. Really interesting. I love to see all the different Earth systems processes, coming together. That's the thing I really love. I was curious if you're familiar with work from John Tarduno's sphere and the inner core nucleation, and if the timing of inner core nucleation could have anything to do with mid-Proterozoic stalling, or even the warming under the continents during steady state, or the decrease in surface evolution that's interpreted during this time, and if there are any connections there that potentially could be examined in the future.
Yeah, Daniel, thank you for your question. I am familiar with John Tarduno, Rich Bono, and others' work on inner core nucleation. I would throw out, part of the reason Dave and I chose not to put paleointensity, which is often used as a proxy for inner core nucleation. The reason we didn't use that here is there aren't as many intensity data as there are inclination data, which I did show. That database is in its relative infancy relative to paleomag inclination. And the other thing right now, Tarduno and others' idea of an Ediacaran age nucleation would be quite late for any match with this mid-Proterozoic interval. But there's a lot of evidence from the seismic community and others that the inner core might actually have 2 layers. I think going forward, we need to reinterpret the intensity data in terms of maybe a 2-phase inner core nucleation. There's by no means, there's basically Andrew Biggins' camp, which argued in a Nature paper for nucleation around 1.3, 1.4, and Tarduno's camp much later. There is really no consensus on the age of the young inner core, plus this complication of there's potentially a 2-step evolution. So absolutely, I think going forward, figuring out, are there 2 phases? When are those 2 phases? And do they play a role here?
Thank you. Really interesting to think about.
Cheers.
All right. Next up was Jingjun Liu.
Hi, Ross. Thanks for your very nice review, and shout out from third floor KGL. I have a question, maybe also related to what Michael published in 2019. I see him also in the audiences, that he was basically arguing that the stability of the subduction was related to the sediments accumulated in the continent, which serve as a lubrication. So I just wonder the balancing torque that forces, whether that can change the thinner layer above the mantle, whether that can change the stability of the subductions.
Yeah, great to see someone working nice and early in KGL, Leo Lausche, and yeah. So Mike's Nature paper, Sobolev and Brown, totally an element in here where if you aren't lubricating the subduction zones, okay, you're not going to get this kind of dramatic high pressure conditions. So there's absolutely reasons to mechanisms to start integrating the supply of sediments to the tectonic processes, to the crustal metamorphic levels. This is the next step. So thank you for. I originally was hoping that we could have more mechanisms in this talk, but before doing that, I really kind of wanted to just see how all the proxies lined up. So I think going forward, that is exactly the kind of thing we want to look at. Is what is it top down? Is it bottom up? What are, in that case, that would be a top-down mechanism where for some reason sediment supply is higher or lower, and that's going to show up in according to Mike's model in the metamorphic record. So excellent question.
Oh, thanks.
So next we have Zheng Gong.
Hi, Ross. Really interesting talk. I just want to ask a more detailed question about the inclination data. you show that the mid-Proterozoic data, there's a lot of low inclination data, but what that paper doesn't show is the error bar for the middle part. And also they don't show like how many like sedimentary data they include in this bin. But let's just assume that this low inclination is real. What do you think? Like why the balanced billing will give you more low inclinations?
Funny coming from you, who wrote a paper in geology last year saying that the Mid-Proterozoic is dominated by a dipole. Thank you, Zhengong, for your question. Again, people, I would refer you to his excellent geology paper with David last year, kind of reinforcing the dominance of the dipole. But the next step is how dipolar is dipolar. Sure, in terms of data, sedimentary inclination shallowing, if their data are biased by a lot of sedimentary rocks, that would be a problem. But the fact that there are very few passive margins during that time, I would probably believe that there are not many, there's probably not much of that bias in there. I think it's tough because we haven't, to your paper and to David's, evaporates paper, there's really no convincing evidence to kind of, relinquish the dipole. But the question is do we really have, moving forward, can we get the precision to ask the further question, how dipolar is dipolar? But again, you could actually have an inclination bias, not simply by a geomagnetic thing. You argued for an artifact from the types of rocks. There's also an artifact by tectonics. Okay, today we have continents at the South Pole, like Antarctica and Greenland at the North Pole. But what if tectonically, for whatever reason, in this balanced convection plan, what if for whatever reason we didn't actually have a continent scattered around the globe? So with this concept of maybe incomplete breakup, if you don't break up all the continents 90 degrees away from Africa, like we did in Pangaea, maybe you don't actually disperse continents to latitudes like Greenland and Antarctica. So I'm personally unconvinced that it's a problem with the geomagnetic field, but it's obviously something we need to consider.
So it can be a surface proxy instead of a core proxy, right? That's what.
Could be. But what I would argue, if it's based on tectonics or a combination of tectonics and true polar wander, having continents stay at lower latitudes, that's going to be controlled by mantle convective planforms, which go all the way down to the core. So even if it is a tectonic continental arrangement thing through tectonics and TPW, it could still be arguably controlled by processes with mantle convection all the way down to the core.
Okay, thank you.
Okay, I've got nothing else here, but I did notice, David, you had a hand go up, but then went down. Are you all good?
Yeah, fine. I was just going to say the same thing that Ross just said.
Okay.
Lots of great suggestions for alternative names go on in the chat as well. I don't know if, so, but to my mind, if you call it stable, I think that represents, if something is stable, it represents a balance. It doesn't have to be a one-dimensional, doesn't have to be two opposing forces. It could be multiple opposing forces in different dimensions, whether you think of them as physical forces or inputs and outputs of a chemical system or anything like that. So yeah, but I see a new chat from Shihong, which seems really interesting. So I'd love to hear more about that.
Yeah, so yep, there's a question in the chat from Shihan Zhang. It's time of the interval is interesting, between 1.8 and 0.8, or between 1.75 and 0.75, or 1.9 and 0.9. In fact, we do not know the age of the Neoproterozoic. oxygenation event, and know little about between 1.3 and 1.0. Is that correct? Ross.
Yeah, so Zhang Shihong, 谢谢. Thank you for your question. Good question. So in the figure, as you can see with the reprints that I sent the link at the top, if we decide as a community that this is an interval worth establishing, we're gonna have to argue about what the basal boundary is and what the top boundary is. And so right now, I just took kind of what conventionally people had referred to in the past, the disappearance for the last appearance datum of banded iron formation around 1.83, the Gibraltar Formation, Slave Craton. So that's the last gasp of banded iron formation as the boundary, the lower boundary, and the top boundary previously probably would have been the Bitter Springs anomaly, the first Neo-Proterozoic carbon isotope excursion. But 2 years ago, we found an earlier carbon isotope excursion around 940, the Magiatois anomaly. It's only been defined in North China, Graham Shields would remind me. So whether that's truly global or local, remains to be shown. So at least now in our first iteration, those were kind of the lower and upper boundaries that we used to argue for this interval. But again, kind of like defining these Proterozoic boundaries, which are very controversial, which proxies you use, especially when they're occurring throughout the Earth system, it's, next level questions. Thanks, Shihong.
All right, next, Greg Vitalik has his hand up. Or Shihong, did you want to say something else? Sorry about that. Maybe not. Okay. All right, Greg, please go ahead.
Thanks. Great talk, Ross. I really enjoyed it. The discussion on inclination twigged, I thought that perhaps it's related to change in the geoid. Is that possible? I have no expertise in this whatsoever. But what if the Earth got fatter, more spherical?
Absolutely. Yeah. So apologies for not including a soils proxy, Greg.
Oh, no problem. I have no ideas about all of this.
That'll be our next iteration. So actually, I don't know if you heard Zheng Gong's question. The end of his question, I kind of got to that. Maybe the continents aren't going to high latitudes, and the reason they would do that, if maybe they aren't dispersing to high latitudes, restricted to low latitudes, maybe because mantle convection is convecting in such a pattern in a plan form where, maybe in downwelling, instead of being like a ring of fire like we have today, maybe it's like an equatorial downwelling where all the continents are, flowing downhill. So the Earth is a different shape from a mantle convective point of view. The geoid would have been different. The mantle, so the gravity would have been different. The seismic structure would have been different.
Well, yeah, my thought is that the geoid might have been more spherical, not oblate anymore. I mean, is there any evidence for that or any way to get at it?
Well, so if today, as everyone knows, Earth is highly non-spherical because we're this oblate or even prolate spheroid, the two upwellings underneath the Africa and the Pacific. If Earth was more oblate, okay, where there's more upwelling, not just in the Africa and the Pacific on the equator, but kind of more around the whole equator, or if Earth is more spherical, less triaxial or less biaxial, that could also, especially if the mantle is balanced in the upwellings and downwellings, then the shape overall, the non-hydrostatic shape, as we call it, would be more spherical, or at least less prolate, less like an American football, less like a rugby ball like it is today.
Mm-hmm. Fascinating. Thanks.
Cheers.
All right, Andre, you go ahead.
Yeah, nice talk, Ross. I don't like name boring, but sort of balanced also doesn't attract me so much for reason that you know, it's sort of philosophical question if you want to lump things in a broader interval or divide it. But I mean, if you think about Phanerozoic, certainly it was balanced. But when were events like ocean anoxic events or glaciations or evolution in life, but these are events on the top of generally like balanced carbon cycle or whatever. And so I would argue that through Earth history, there are multiple states of balance that perturbed by various events. And so maybe we should focus more on different modes of operation of forces that sort of results in this shift from one balanced state to another balanced state, rather than just a single out balanced state through Earth history. And I guess by selecting mode of operation, it would be somewhat subjective, but eventually that's what we want to get to.
Awesome point, Andre. I think David, I don't know if everyone can see David Evans's background, but I think he's chosen it specially for today, this tightrope walker. I agree with you, Andre, that, you know, there's balance and then there's balance. Okay. Even if you have, you know, you could argue that, you know, going from the super high stock market of the 1920s, you know, the golden age, to the Great Depression, that high and that low, sure, over that cycle, there's balance. But is that with that volatility, is that the way you want to do a tightrope walk? You know, if your focus is really balance, is that level of volatility the way you want to do it? And obviously, you know, from Dave's tightrope walker, you know, that's not, if balance is the goal, you want to minimize volatility. So there was a nice message from Leanne Reedman about new eukaryotic diversity data. I saw some of the data present also by Max Letke, Goldschmidt, where people are seeing more and more a level of eukaryotic diversity as they go through, you know, sequence by sequence of these mid-Proterozoic sequences. Still, I would say, you know, power to you, but at the end of the day, how does that compare to a Cambrian explosion? How does that compare, you know, to the ecological dominance of eukaryotes in the late Proterozoic, early Phanerozoic, and the diversity? So it's all relative. And I think, you know, the reason you know, maybe volatility, maybe balanced isn't perfect is because we're really kind of talking about reduced volatility. And I'm sure if there was a financial expert on the call, they could help us, you know, for what term that might be. But, you know, at least in a cyclostratigraphic approach, you know, your amplitudes wax and wane. And, you know, in these nodes of eccentricity, for example, your precession, the precession's always changing, but only when eccentricity is high does the precession change a lot. So I think, you know, better than, I mean, if there's any reason boring might have been good, it's because it touched on the lack of volatility. Yes, there's diversity, but is there diversity in the sense of the Cambrian explosion? Yes, there are, someone commented earlier on there being some iodine excursions, which are related to oxygenation. And yes, people are, you know, my colleagues here in Beijing are arguing for Mesoproterozoic oxygenation events, but they're not orders of magnitude like the GOE or later. So I think magnitude is something to keep in mind, which the balance does well. If you are trying to be the tightrope walker, you're not going to want to be doing this. You're going to want to be doing this.
But you would not define I guess Cambrian explosions to some degree define Phanerozoic, but you wouldn't characterize Phanerozoic by Cambrian explosion. It's a transition period to kind of like a new steady state. And so in a way, I guess what you may be implying with Mid-Proterozoic is a time kind of unconsequential experiments. So it's like were attempts of oxygenation or maybe rifting, but we did not result in a shift from one sort of steady state to another steady state.
I love that, Andra. Even if you don't like the phrase balanced for the balanced billion, I think your larger point is balance is a concept for us to apply to all of Earth history. Are we going from one balance to another balance to another? And that's going right back to, kind of that Dick Holland kind of stage one, stage two. So I agree with you that the balance theme here is kind of larger than the balanced billion.
Thanks.
Yeah, I see our hand up, Greg, but I think I want to peg on Andre really quick. Do people hear me? Yeah. Okay. I think, yeah, I wanted to step up and mention, I think the term boring also hasn't been great, and a lot of people have bounced off this word in titles of publications and how they want to talk about, like you mentioned earlier, the not so boring billion, etc. But it is interesting to see, like, I'll mention that Leanne Reedman pointed out in the chat that as people continue to publish on this time period, we see a lot more diversity in the early eukaryotic fossil record, or the fossil record, throughout this time period. And maybe before it was, we had this idea of low diversity based on lack of sampling or lack of study in it. And you mentioned sort of the last gasp of iron formation, but I know we have some happening 1.6, 1.4 from the North China Craton. So I think we're finding things that we used to base this word boring on that certainly call for probably an end to this term boring. But it is interesting to think about how those play into a new word like balanced. And I think Andre said a really interesting term there, unconsequential experiments, which you can think of in a biological term, or experiments of how to try and maybe do something for something sedimentological to happen. But that to me, that actually seems to ring something that might be interesting to think about during this period, because we do see a bunch of things that just didn't happen to cause the Cambrian explosion. So that's more of a comment rather than any question involved, but that was kind of building in my mind while I was watching your presentation.
Oh, neat thoughts, Alex. Yeah.
Yeah, so Greg, please go ahead.
Yeah, just riffing off your comment that you didn't do anything about paleosols made me think what was good about paleosols. I don't know if you saw my paper a couple of years ago on paleosols of the Ruyan group, and thinking about it, going way back with Dick Holland on the Heckport paleosol, which everybody and their dog is published on. I'm from a paleosol perspective, I think we should relabel the boring billion the beautiful billion, because this is when this is the beautiful billion. Yeah, because this is the first time when we get sols that we can finally understand. The Archean is just weird. I had a paper drop in PLOS One today, actually, on the Archean of the Pilbara, and I've had several papers on the Archean paleosols. They're weird. But the first vertisols, the first really nice, thick paleosols turn up around about 2.1 and go right through that interval without too much diversity. The diversity comes in the Neo-Proterozoic and particularly in the Devonian. Yeah, from a paleosol perspective, it's the beautiful billion.
Well, that stays with the alliteration, so that's a viable
We need to
candidate.
keep the alliteration going, I think. Yes, it's tradition.
Really. Just get out your dictionaries and go through the B's. Everyone will have their own billion tomorrow.
Yeah, probably. Anyway,
That's
very
fascinating, Greg.
stimulating. Yeah.
No, and absolutely, as a critical, as a critical boundary condition, I'm kind of, a little embarrassed to say that we didn't include, a soil layer. So, that's something that I'll be in contact with you about.
Yeah, great. Thanks.
All right, there's nothing else here. It's particularly late for you over there, so maybe we can let you catch some shut-eye.
It's now Mid-Autumn Festival.
Yeah, enjoy. All right, thanks everybody for a great first round for the fall. And we'll see you next Thursday.
Awesome. Thanks, Alex. Thanks, Andre.